Chapter 5 jumps around a little bit. We just did 5.1 was derivatives of natural logs, and 5.2 was the antiderivatives of natural logs. Now we're going back to derivatives, but we're not taking derivatives of particular functions. We're taking a look at just inverse functions in general. So before we talk about inverse functions, we're going to, or before we talk about the calculus behind it, let's make sure we remember what an inverse function is. So first of all, inverse functions exist only if the original function is 1-to-1. 1-to-1 meaning not only for each x is there only one y, that's what a function is, but also for each y there is only one x. Another way to put this is not only does it pass the vertical line test, but the function passes the horizontal line test. We can write inverse functions using the -1 exponent. We're not raising anything to the -1. That would be taking the reciprocal. But it looks the same as raising to the -1. F inverse of x is the way we would write that. And the whole point of an inverse is it undoes the original function, right? So if I plug in an input and I get an output of the original function, if I take that output and I plug it into the inverse will undo everything until we get back to the original input. And that's the idea right here. X gets plugged into g, we get some sort of output, but then the inverse undoes that output and takes us back to x. And the reverse is also true. G of f of x is also equal to x. So the whole rule about inverse functions is we're switching the inputs and the outputs. We're switching the x's and y's. So if we define our function as being just a discrete set of points, then f inverse would be another discrete set of points, and 2, 5 would become 5, 2. And 3, 6 would be 6, 3. And -1, 2 would become 2, -1. And 4, 7 would become 7, 4. Easy peasy. Okay, we switch the x and the y. Now, if we're looking for the inverse of an equation, we remember that the output is generally, we'll call that the y value, and we'll say that y equals 5x minus 8. So if we're interested in the inverse, maybe I'll switch colors to indicate this is a new equation, and the x value becomes the y value, and the y value becomes the x value. The input and the output swap. So if we're going to figure out what this new output is, it's the old input, we're going to solve for y in this new equation. So we'll add 8 to the other side. That's equal to 5y, so we'll divide by 5 and get y. Or another way we could write this is f inverse of x equals 1/5 x plus 8/5. Okay. Graphically speaking, same idea. We're just going to flip the x's and y's. So if I give you a graph and I ask for the inverse of that graph, invert each point. So the point -3, -5 is going to invert to the point -5, -3. The point -1, -4 is going to invert to -4, -1, and 0, -2 goes to -2, 0. 1, 1 doesn't move because the x and the y are the same. And 2, 3 goes to 3, 2. 5, 4 goes to 4, 5. And then we do our best to connect the dots the same way they were connected before. So this is a nice smooth curve approaching perhaps a point of inflection. So we'll go like this. And then it will go like this. Something like that. Looks like some forceps, maybe. Some sort of medical tool, or maybe some tongs to pick up burning wood out of a fire. I don't know. Anyway, so that's what the graph of a function and its inverse might look like. Pay attention to the symmetry here. There's a line of symmetry. It's the line y equals x. Y and x just flip. So we're going to flip over the line y equals x. Notice that where the function and its inverse intersect are the same places where they intersect the line y equals x. That's not a coincidence. And so that's an interesting thing to note. So I'd like to call attention to the slope here. Since we're talking about calculus, we're probably going to be talking about derivatives. If we look at the slope of the equation given in part B here, we all know that that slope is 1/5, right? Oop, I'm jumping ahead. It's 5. The slope of its inverse is 1/5. So take a look. This might not be surprising, but the slopes are the slope of f of x, is 5, and the slope of f inverse of x is 1/5. They're reciprocals, right? And I don't think that's surprising when you think about how all the x and y information switch. All of the x and y information switch. So remember what the slope is. The slope is delta y over delta x, the change in y over the change in x. So we're just going to have to flip-flop the rise and the run, the x and the y. So it's going to change that by taking the reciprocal of it. Indeed, you can kind of see that in this graph as well, right? Perhaps you might notice that the slope from this point to this point was 1/2, but the slope from this point to this point was 2. Anywhere where we had a very small slope, like close to 0, this is where we're going to have a very steep slope, like close to infinity. Okay, so these are some relationships that I hope are not terribly surprising when we look at the slopes of inverse functions. All right, so let's take a look at a concrete example. The square root of x is a pretty easy one to work with. Let's take a look at some individual points on the graph f of x equals the square root of x. If x equals 1, then y equals 1. If x equals 4, then y equals 2. If x equals 9, then y equals 3. These are all just points on our familiar square root curve. All right, and now it asks us to find the slope at those particular points. And of course, in order to find the slope, we need to find f prime of x. But we know how to find the derivative of the square root of x. We'll take the power rule, and I might rewrite this as 1 over 2 root x. So I'm going to evaluate the slope at when x equals 1. It'll just be 1 over 2 root 1, or 1/2. That's the slope right here. And the slope when x equals 2 is 1 over 2 root 4, or 1 over 2 times 2, which is 1 over 4. So that's the slope here. And then finally at 9, 3, we're going to get a slope of 1/6. Okay. It shouldn't be terribly surprising that as we progress from left to right, our slope is going to decrease from 1/2 to 1/4 to 1/6, etc. All right, so now we want to consider the inverse function. Well, we're going to take 1, 1 and flip the x and the y. We're going to take 4, 2 and flip the x and the y. We're going to take 9, 3 and flip the x's and the y's. In fact, we're going to take the equation y equals the square root of x, and we're going to flip the x and the y. And then if we wanted to solve for y, we get y equals x squared. So just when x is positive, because x was only positive in the original function, we get the positive half of our standard parabola, right? So it'll look something like this. And again, the line y equals x would be your axis of symmetry there. All right, well, what is the, this is f inverse, right? F inverse of x is equal to x squared. So now we're asking to find the slopes of the corresponding points here. Well, let's take a look. F prime inverse of x. Well, that's an easy one to do, right? That's just 2x, one of the easiest derivatives there is. So we'll take x equals 1, the slope is 2. When x equals 2, the slope is 4. When x equals 3, the slope is 6. Note that relationship between corresponding points. The inverse function has reciprocal slopes at its corresponding points. And that is the key to this whole section.